Ever wonder why some engines become legends while others fade into obscurity? Why certain power plants inspire an almost religious devotion decades after production ends? The Nissan RB26DETT isn't just an engine, it's a cultural phenomenon, a piece of engineering that rewrote the rules of what a production motor could do. Today we're diving deep into 20 shocking secrets about this twin-turbo monster that even die-hard JDM fans probably don't know. From hidden factory capabilities to engineering tricks that wouldn't appear in other engines for decades, we're exposing the truth behind Japan's most mythical power plant. So buckle up, because what you're about to learn will change how you see this legendary engine forever. Number 20. The RB26DETT was never officially sold in the United States, making it one of the most mythologized Japanese engines ever created. Think about that for a second. An entire generation of American enthusiasts grew up worshiping an engine they couldn't legally own. It was forbidden fruit, the ultimate tease. While Europeans and Australians were getting their hands on Skyline GTRs, Americans were stuck reading about them in magazines, watching grainy VHS videos of them dominating on Japanese mountain passes. The 25-year import rule became a countdown timer for enthusiasts. Forums exploded with speculation. How much power could it really make? Was it as reliable as everyone claimed? The mystique grew stronger every year. When the first R32 GTRs finally became legal in 2014, prices went absolutely insane. People were paying $70,000 for 25-year-old cars, all because of that engine. The RB26 became more than just hardware. It became a symbol of everything Americans were missing out on. The grass really was greener on the other side of the Pacific, and Nissan knew it. They teased us with concepts, showed GTRs at auto shows, but never sold them here. That exclusivity made the legend grow even stronger. Number 19. Its name actually decodes as RB, meaning race bred, 26 for 2.6 liters displacement, DE for dual overhead cam with electronic fuel injection, and TT for twin turbo. Every letter and number has meaning. Nothing was arbitrary. Nissan's naming convention tells you exactly what you're dealing with. Racebred wasn't just marketing fluff either. This engine was literally bred for racing from day one. The entire RB series was developed with competition in mind. But the 26DETT was the pinnacle, the ultimate expression of that philosophy. 2.6 liters might seem small by today's standards, but in 1989 it was the perfect balance. Big enough for serious power, small enough to stay within racing regulations. The dual overhead cam setup was cutting edge for a production engine, 4 valves per cylinder, variable valve timing on later versions. Electronic fuel injection was still relatively new technology. Most performance cars were still running carburetors or primitive injection systems. The RB had sequential multi-port injection, sophisticated for its time. And those twin turbos? They weren't just bolted on as an afterthought. The entire engine was designed around forced induction from the beginning. Every component was engineered to handle boost. Number 18. The iron block was massively overbuilt for racing with thick cylinder walls, 6-bolt main bearings, and a closed deck design that could handle over 1,000 horsepower with modifications. This wasn't accident. Nissan knew exactly what they were doing. While other manufacturers were trying to save weight with aluminum blocks, Nissan went old school. Iron. Heavy, yes, but bulletproof. The cylinder walls were thicker than they needed to be for stock power levels, way thicker. Engineers designed them to handle extreme cylinder pressures, the kind you get when running 30 pounds of boost. 6-bolt main caps were overkill for a street engine. Most production engines use 2 or 4 bolts. But Nissan wanted zero flex in the bottom end, even under extreme loads. The closed deck design meant the cylinder walls were fully supported at the top. No open water jackets to create weak points. This is race engine architecture, the kind of design you'd expect in a purpose-built competition motor, not something sold in dealerships. Tuners discovered they could bore and stroke these blocks way beyond factory specs. 3 liters was common, some went even bigger. The iron could take it. Modern engines with aluminum blocks can't handle that kind of abuse. They crack, they warp. The RB just asks for more. Number 17. Factory pistons and connecting rods were forged, which was extremely rare for production engines of that era. Stop and think about that. In 1989, most performance cars had cast pistons, even exotics. Forged internals were race car territory, aftermarket upgrades, not standard equipment, but Nissan equipped every single RB26 with forged pistons from the factory. Not cast, not hyper-eutectic, forged aluminum. The connecting rods? Also forged steel, not powder metal, not cast. Proper forged pieces that could handle double the factory power without breaking a sweat. This wasn't cost-cutting. Forged components cost significantly more to produce. Nissan was essentially giving buyers race-spec internals as standard equipment. Why? Because they knew owners would modify these engines. They knew tuners would push them to the limit, so they built them strong from the start. The factory pistons could handle 20 pounds of boost reliably. The rods were good for 8,000 RPM all day long. Most owners who rebuilt their RB26s kept the factory rods, just added better rod bolts. That's how good they were. Even today, 35 years later, those factory-forged internals are still sought after. People building RB26s specifically look for original pistons and rods. They're that good. Number 16. The engine revved to 8,000 RPM stock, aided by a fully counterweighted crankshaft that provided silky, smooth balance. 8,000 RPM from a 2.6-liter engine in 1989 with hydraulic lifters. That was unheard of. Most engines that size were redlining at 6,000, maybe 6,500 RPM. The RB laughed at those numbers. It wanted more. The secret was that crankshaft. Fully counterweighted, every journal perfectly balanced, no harmonics, no vibration, just smooth power delivery all the way to redline. Nissan didn't just balance the crank either. They knife-edged it. Reduced windage, less parasitic loss. Every little detail mattered. The valve springs were dual units, stronger than single springs, better at high RPM, less valve float, more precise valve control. Even the camshafts were special, hollow construction to reduce weight. Less reciprocating mass meant the engine could rev faster, build RPM quicker. But here's the really crazy part. That 8,000 RPM redline was conservative. The engine could safely spin to 8,500, even 9,000 with minor modifications. Nissan just didn't want warranty claims, so they set the limiter low. Tuners immediately raised it, and the engines took it. No problems. Try that with a modern turbocharged engine. Most will scatter themselves across the pavement. Number 15. Sequential twin turbos provided a broad power band where a small primary turbo spooled early and a larger secondary turbo joined at higher RPM, except that's not how the RB26 worked at all. Common misconception, even among enthusiasts. The RB26 used parallel twin turbos, not sequential. Both turbos were identical, both spooled at the same time. Each one fed 3 cylinders. The confusion comes from other Japanese engines of the era. The Toyota Supra used sequential turbos. So did the RX-7. People assume the RB did too. Nope. Parallel setup. But here's what's interesting. Nissan's parallel setup actually worked better than sequential systems in many ways. More linear power delivery, less complexity, better reliability, no complicated changeover valves, no vacuum lines to fail, just 2 turbos doing their job simultaneously. The small turbo size meant quick spool-up, almost no lag. By 2,500 RPM, you had boost. full boost by 3,000, and it pulled hard all the way to redline. The power delivery was addictive, not peaky like big single-turbo setups, not laggy like sequential systems during changeover, just smooth, consistent thrust. Many tuners actually preferred the parallel setup. It was predictable, easy to tune, easy to modify. Want more power? Just upgrade both turbos equally. Simple. Number 14. Japan's Gentleman's Agreement limited advertised power to 276 horsepower, but dynos consistently showed closer to 320 horsepower from the factory. The biggest lie in automotive history. Every Japanese manufacturer agreed to limit advertised power, keep the government happy, avoid stricter regulations. But nobody actually followed the rule. Nissan was probably the worst offender, or best, depending on your perspective. They claimed 276 horsepower at the crank. Every GTR owner knew that was nonsense. Dyno tests proved it. Stock RB26s put down 260 to 280 horsepower at the wheels. Factor in drivetrain loss, and you're looking at 320, maybe 330 at the crank. Some engines were even stronger. Hand-built motors have variations. Some were absolute monsters from the factory. There are documented cases of stock engines making 300 wheel horsepower on stock boost, stock turbos, stock everything. Nissan's engineers were basically building race engines and detuning them on paper only. The hardware was capable of so much more. They just lied about it. And everyone knew. Journalists knew. Competitors knew. The government probably knew too. But nobody said anything. It was an open secret. The 276 horsepower club was pure fiction. Marketing departments were having a laugh while engineers built absolute weapons. Number 13. Ceramic turbo turbine wheels saved weight but were incredibly fragile at high boost, leading most tuners to immediately swap in steel versions. Ceramic turbine wheels. Sounds high-tech, right? Lightweight, exotic, Formula One technology. In reality, they were a ticking time bomb. The ceramic material was indeed lighter than steel, about 60% lighter. Less rotational mass meant faster spool-up, better transient response. In theory, perfect. In practice, disaster waiting to happen. Raise the boost past 15 psi, and those ceramic wheels could shatter, literally explode. Send ceramic shrapnel through your engine, through your turbo housing, sometimes through your hood. The problem was heat cycling. Ceramic doesn't handle rapid temperature changes well. Hard pulls followed by sudden deceleration. The exact type of driving GTR owners did. The wheels would develop micro cracks, eventually catastrophic failure. Tuners learned this lesson quickly. First modification on any RB26? Steel turbine wheels. Didn't matter if you were keeping stock boost. Those ceramics had to go. They were a liability. The steel wheels were slightly heavier, marginally slower spool, but they could take abuse. 30 pounds of boost? No problem. Repeated drag runs? All day long, the ceramic wheels became legendary for all the wrong reasons. People still find RB26s with original ceramic turbos. They're treated like unexploded ordnance. Handle with extreme care. Number 12. The oil pump drive on early engines was undersized, causing failures above 8,000 RPM until Nissan quietly revised it. This was the RB26's Achilles heel, the one real weakness in an otherwise bulletproof design. And Nissan never officially acknowledged it. The oil pump drove off the crankshaft through a small collar. That collar was the problem. Too thin, too weak, not enough meat to handle the stress. Rev past 8,000 RPM repeatedly and it would crack. When it cracked, oil pressure disappeared instantly, no warning, just sudden, catastrophic engine failure. Spun bearings, seized pistons, complete destruction in seconds. The racing teams discovered this first. Engines were failing during endurance races. Always the same failure mode. Oil pump drive collar. Nissan quietly redesigned it, made it wider, stronger, better material, But they never recalled the early engines, never issued a service bulletin. Owners found out the hard way. Forums lit up with horror stories. Beautiful engines destroyed because of a $50 part. The aftermarket stepped in, billet collar upgrades, crank collar support kits. Every serious RB26 build now includes an upgraded oil pump drive. It's mandatory. Even Nissan's fix wasn't perfect. The revised collar was better, but still not ideal for extreme use. 9,000 RPM plus high oil pressure could still cause problems. The design flaw became part of RB26 folklore. Everyone knows about it. Everyone fixes it. It's just part of the ownership experience. Number 11. It featured 6 individual throttle bodies, 1 per cylinder, for absolutely razor-sharp throttle response. Individual throttle bodies, ITBs, the holy grail of naturally aspirated response. But on a turbo engine, that was unusual, almost unheard of. Most turbo engines use a single throttle body, simpler, cheaper, easier to package, but Nissan went full race car with the RB26, 6 throttle bodies, 1 for each cylinder. The complexity was staggering. 6 butterfly valves, 6 throttle position sensors, all synchronized, all working in perfect harmony, or at least they were supposed to. The throttle response was telepathic. Touch the pedal, and the engine responded instantly. No delay, no lag, just immediate reaction. It made the car feel alive, connected. The sound was incredible too. 6 throttles opening simultaneously created this mechanical symphony, a metallic whoosh that no single throttle body could replicate. But synchronizing them was an art form. Get it wrong, and the engine ran terribly. Rough idle, poor fuel economy, inconsistent power delivery. Shops charged hundreds of dollars just to sync ITBs properly. Special tools were required, vacuum gauges for each throttle, hours of careful adjustment. Many owners gave up. Converted to single throttle body, simpler, more reliable. But they lost that special feeling, that immediate response, that race car character. The ITBs were what separated the RB26 from pretenders. Number 10. The cylinder head design was so efficient that Nissan reused its flow principles in later engines, including the VR38DETT. That head was a masterpiece, 20 years ahead of its time. The port design, the combustion chamber shape, the valve angles, everything was optimized for maximum flow. Nissan spent millions developing it. Wind tunnel testing, computational fluid dynamics. Except they didn't have CFD in 1985. They did it old school. Flow benches, trial and error, hundreds of prototypes. The intake ports were straight shots. No weird turns, no shrouding, just smooth, efficient flow paths. The exhaust ports were equally impressive, large diameter. Smooth transitions, minimal restriction, even at high flow rates. The combustion chambers were pent-roof design, ideal for flame propagation. The spark plug was centered perfectly, even burn, maximum efficiency. The valve angles were optimized for flow, not packaging. That's why the head was so tall, so wide. It barely fit under the R32's hood. When Nissan developed the VR38 for the R35 GTR, they started with the RB26 head. Same basic architecture, same design philosophy, just scaled up, modernized. They admitted it publicly. The RB26 head was so good they couldn't improve on the basic concept, just refine it. 20 years of advancement and the fundamental design remained unchanged. That's how far ahead the original was. Number 9. Atessa ETS all-wheel drive and Hikas four-wheel steering worked seamlessly with the RB26 and the Skyline GTR. The engine was only part of the equation. The RB26 was brilliant, but it was the complete package that made the GTR legendary. Atessa wasn't just all-wheel drive, it was intelligent all-wheel drive, computer-controlled, constantly adjusting, predictive. The system could send 100% of power to the rear wheels, like a drift machine, or split it 50-50 when you needed maximum traction, all controlled by computers that monitored wheel speed, steering angle, throttle position, and G-forces. In 1989, when most cars still had mechanical distributors, the Heikes four-wheel steering was equally advanced. The rear wheels could turn up to 1 degree. Doesn't sound like much. But it transformed the car's behavior. High-speed stability improved dramatically. The car felt planted, confident. Low-speed agility was enhanced too. The GTR could change direction like a much smaller car. All this technology working together with the RB26 created something special. The engine provided the power. Atessa distributed it perfectly. Heikes kept everything pointed in the right direction. It was a symphony of technology, each system complementing the others. The result was devastating performance. The R32 GTR destroyed everything in its path. Porsches, BMWs, even Ferraris struggled to keep up. Number 8, it powered the R32, R33, and R34 GTRs, making it synonymous with Japan's Godzilla legend. 3 generations, 13 years, one engine. The RB26 defined an era. Each generation got refinements, improvements, but the core engine remained the same. The R32 was the pure one, raw, visceral. 8,197 examples built, each one a legend in its own right. The R33 was the refined one, bigger, more comfortable, better aerodynamics. But enthusiasts initially rejected it. Too soft, they said, until it set a production car lap record at the Nürburgring. Then attitudes changed. The R34 was the ultimate evolution, the perfect GTR, everything learned from 2 generations distilled into one car. 11,300 examples, the last of the RB26 dynasty. Each generation pushed the engine further, better cooling, stronger internals, more sophisticated management. But the basic architecture never changed. That original design was so good it didn't need revolution, just evolution. The Godzilla nickname came from Australian media. The R32 was dominating their touring car championship, destroying V8 Holdens and Fords. They called it a monster. Godzilla, the name stuck. It was perfect. A Japanese monster crushing everything in its path. The RB26 was Godzilla's heart, its soul. Without that engine, there would be no legend. Number 7. Nismo hand-built race versions for Group A and N1 endurance racing that produced over 600 horsepower reliably. Nismo, Nissan Motorsports. These weren't just tuned street engines, they were different animals entirely, hand-assembled by master technicians, each one a work of art. The Group A engines were restricted by regulations, but Nismo found every loophole, every advantage, blueprinted everything, balanced everything. The result? 400 horsepower from 2.6 liters with restrictor plates on pump gas. The N1 engines were even more special, built for 24-hour endurance racing, 600 horsepower for 24 hours straight, at full throttle, no brakes. These engines used different pistons, different rods, different cams. Everything was upgraded, but it was still recognizably an RB26, the same basic architecture pushed to its absolute limit. Nismo's engineers learned valuable lessons from racing: better oil circulation, improved cooling, stronger valve springs. These improvements trickled down to street cars. The N1 block became legendary among tuners, stronger than standard blocks, better cooling passages, worth its weight in gold on the used market. Nismo sold these engines to privateer teams, 5 million yen each, in 1992 money, but teams paid it gladly, because they won races, dominated championships. The reliability was staggering, engines running 24 hours at 9,000 RPM, coming back for the next race. No rebuilds, just basic maintenance. Number 6, the R32 GTR with RB26DETT won 29 consecutive Group A races, forcing Australian regulators to essentially ban it. 29 races in a row, total domination. The Australian Touring Car Championship had never seen anything like it. From 1990 to 1992, the R32 GTR was unbeatable. Jim Richards and Mark Skaife made history. The Gibson Motorsport GTRs were weapons. V8 Holdens and Fords had ruled for decades. Big displacement, big power, Australian muscle. Then came the GTR, smaller, lighter, all-wheel drive, sophisticated. The V8 teams complained immediately. It's not fair, they said. Too much technology, too advanced. The fans were divided. Some loved seeing new technology. Others wanted their V8s to win. The racing was incredible, though. GTRs dancing through corners, V8s powering down straights. Different philosophies battling it out. But the GTRs kept winning, and winning, and winning. The rule makers tried everything. Weight penalties, boost restrictions, tire limitations, nothing worked. The GTRs adapted, kept winning. Finally, they changed the rules entirely. 2-liter turbo limit, effectively banning the RB26. The GTR was too successful for its own good, but those 29 victories cemented the legend. David had slayed Goliath 29 times in a row. The RB26 had conquered Australia. Even in defeat, it won. Number 5. Tuners discovered the stock block could support 1,200-plus horsepower with upgraded internals and fuel systems. 1,200 horsepower from a 2.6-liter from a block designed in the 1980s. That number seems impossible, but it's real, documented, proven on dynos worldwide. The stock iron block was that strong. Those thick cylinder walls, the 6-bolt mains, the closed deck design, it all added up to incredible strength. Tuners started conservatively. 500 horsepower was easy. 600 required basic upgrades. 700 needed better turbos. Then things got serious. 800 horsepower builds became common. Upgraded pistons, stronger rods, bigger turbos. But the stock block held 900, 1,000. The block didn't care. It just kept taking more abuse. The magic number was around 1,200. That's where things got sketchy. Cylinder walls could crack, main caps could walk. But below that, rock solid. The supporting mods were extensive. Fuel systems flowing 2,000 cc per minute. Turbos the size of volleyballs. Intercoolers bigger than radiators. But the core engine, that 1980s iron block, held it all together. Modern engines with aluminum blocks can't do this. They're lighter, more efficient, but not stronger. The RB26 block became the foundation for some of the fastest cars on Earth. Drag cars running 7s, street cars making 4-digit power, all built on that legendary block. Number 4, many RB26s ended up in Silvias, 240SX, and even Mustangs after Japan's export flood under the 25-year rule. The great RB migration began in 2014. Suddenly, Americans could legally import 25-year-old Japanese cars and engines, lots of engines. Container loads of RB26s arrived monthly, some in GTRs, many as bare engines. The swap culture exploded, RB26 into everything. The Silvia swap made sense. Nissan chassis, similar dimensions, relatively straightforward. The 240SX was America's Silvia. Perfect candidate. RB swaps transformed them from drift missiles to serious performance cars. But then things got weird. RB26 Mustangs, blasphemy to purists, genius to others. Japanese reliability meets American muscle car style. BMW E36s with RB power. German handling, Japanese thrust. The combinations were endless. Some were professional builds, clean, engineered, beautiful. Others were garage hacks, sketchy, dangerous, but running. The engines were surprisingly adaptable. Standalone ECUs made them work in anything. Custom mounts, custom exhausts, make it fit. The sound of an RB26 in a Mustang was surreal. That distinctive turbo whistle, that metallic growl coming from American muscle. It broke people's brains. At car shows, at traffic lights. The confusion was priceless. Is that a 2JZ? No, Is that a V8? Definitely not. It's an RB26 in a Mustang. Because why not? Number 3. The factory ECU ran surprisingly advanced algorithms for 1989 with real-time fuel and ignition trim per cylinder bank. The factory ECU was a technological marvel. In 1989, most cars had primitive engine management, basic fuel maps, simple ignition curves. The RB26 ECU was different, sophisticated, almost intelligent. It could trim fuel for each bank of cylinders independently, detecting lean conditions, rich conditions, compensating in real time, not pre-programmed, active learning. The ignition control was equally advanced, knock detection on each bank, individual cylinder timing adjustment, constantly optimizing for conditions. This was space-age stuff for 1989. Most aftermarket ECUs couldn't match it until the late 90s. The ECU could detect sensor failures, run in limp mode, protect the engine. It had multiple maps for different octane fuels, different climates, different altitudes, all selectable. The diagnostic capabilities were impressive too. Stored fault codes, real-time data streaming. Technicians could diagnose problems without even opening the hood. But here's the craziest part. The ECU was learning, constantly, adapting to driving style, compensating for wear, getting smarter over time. Modern ECUs do this standard. But in 1989? Revolutionary. Tuners initially struggled with it, too complex, too many parameters, but once understood it was incredibly powerful. The factory ECU could handle significant modifications, bigger turbos, different injectors, just needed recalibration. Number 2. The engine's unique sound, that deep mechanical turbine-like tone, comes from its parallel twin-turbo setup and long, equal-length intake runners. That sound, you know it immediately. Deep, mechanical, industrial. Unlike any other engine, it's not just exhaust note, it's everything combined. Intake, exhaust, turbos, mechanical noise, all creating the symphony. The parallel turbos create a unique whistle, two turbines spinning in harmony, not the single turbo whoosh, not the sequential step, something different. The equal-length intake runners add their own note. 6 runners, identical length, creating resonance at specific RPMs. A hollow metallic sound. The individual throttle bodies contribute too. 6 butterflies snapping open, that mechanical clatter, like a race car warming up. Even the injectors make noise, high-flow units clicking rapidly, adding to the mechanical symphony. At idle, it sounds angry, lumpy, like it wants to attack something. Barely contained violence. Blip the throttle, and it snarls. Instant response, immediate aggression, the turbo spool adding their whistle. Under full acceleration, it's glorious. Deep bass notes from the exhaust, high-pitched turbine sounds, mechanical clatter from the valve train, all perfectly synchronized. The sound changes with RPM, different notes appearing, disappearing, harmonizing. It's automotive music. You can identify an RB26 from blocks away, that distinctive idle, that specific turbo whistle, that mechanical anger. No other engine sounds quite like it, not even close. Number 1. Even today, the RB26DETT remains a tuning benchmark, proof that Nissan's 1980s engineering still terrifies modern performance engines. 35 years old. Think about that. This engine is older than most people reading this, designed when cell phones were briefcase-sized, but it still embarrasses modern engines. Take any current turbocharged 6-cylinder, BMW B58, Mercedes M256, Audi EA839, all impressive engines, all technically superior to the RB26 on paper, but can they make 1,200 horsepower on stock blocks? Can they survive 24-hour races without rebuilds? Can they create the same emotional connection? The RB26 does things modern engines can't, or won't. It's overbuilt, over-engineered, designed without compromise. Modern engines are designed for efficiency, emissions, cost reduction. The RB was designed to win races, period. Everything else was secondary. Tuning an RB26 is like archaeology, discovering what Nissan engineers hid inside, the potential they built in but never fully exploited. Every year someone pushes the RB further. New record, new milestone, new impossibility made possible. 1,300 horsepower now, 1,400 tomorrow. The limit keeps moving. Modern engines plateau quickly. They're optimized from factory, not much headroom. The RB was intentionally held back, waiting to be unleashed. The RB26DETT isn't just an engine, it's a philosophy. Build it stronger than necessary, make it more capable than regulations allow. Let the owners discover its true potential. 35 years later, we're still discovering. And there you have it, 20 absolutely mind-blowing secrets about the RB26DETT that prove why this twin-turbo legend still makes modern engines nervous. From ceramic turbos that literally exploded, to factory lies about horsepower to blocks that could handle 4 times their intended output, this engine rewrote every rule. Which of these secrets surprised you the most? And what other legendary engines deserve this deep dive treatment? Drop your thoughts in the comments below. If you enjoyed this trip into JDM history, smash that like button, subscribe, and hit the notification bell so you never miss our next deep dive into automotive legends. Until next time, keep those turbos spooling.